Good morning. So today I just want to go over examples using normal distribution that we talked about yesterday. Just do as many examples as we can. That's the agenda for today. Okay. So this page that you have here, if you can pull it up in front of you, I have the handout posted on Canvas. So if you go to page 127 in that handout, you can see this table which you will need to solve the problems. Okay. So I assume that you have it in front of you. So let's start with a few examples, which I pasted the problem statement here. So I'll give you a second to read the problem statement, and then we can start. The production of a certain polymer fiber follows a normal distribution with a true mean diameter of 20 microns and a standard deviation of 30 microns. So we have, let's say, if we denote our polymer diameter, if we denote it using X, you can use any symbol, just saying X bar, the average is equal to 20 microns and standard deviation in X is 30 microns. That's given. Compute the probability of a measured value greater than 80 microns. So if you just think about the bell curve, this is for the variable X, and the average is here. Average is 20 microns, and the width of the distribution or the standard deviation is 30 microns. What we are asked to calculate is the probability that X is greater than 80 microns. So if suppose this is 20 and let's say 80 is here, we have to figure out how much of the or what is the chance that X can be greater than 80 microns. So that is what is asked. So if you're writing this, I'll just wait for a second for you to tell me if this problem statement makes sense to you so far. Yes. Okay. Thank you, April. Yeah, you can use that tick mark or reactions to just quickly show instead of even if you don't want to talk. All right. So now, next step, we want to write X is X follows normal distribution. That is already told in the problem. I'm just restating it. Okay. So X minus X bar divided by sigma X, we'll call it Z, follows the standard normal distribution and of course f of Z has a mean of 0 and standard deviation of 1, so that we can use the handout, which is table 4.3 can be used. Like I said in class yesterday, the goal of every problem is to reduce the normal distribution given into a standard normal distribution and then solve the problem using the table and then project it back to the original variables. So it is like saying X greater than 80 microns is the same as saying Z equal to X minus X bar divided by sigma X, which is X minus 20 divided by 30, which is so it's like saying Zx greater than 80 is same as saying Z greater than, wherever X appears, you need to substitute 80. So 80 minus 20 is 60. 60 divided by 30 is 3. So X greater than 80, this is the variable with units. This is the scaled variable. without units. So x, what if you want to ask the question, what is the probability that x has a value greater than 80? It's the same as asking what is the probability that z has a value greater than 2. And from the discussion yesterday, can you tell me how will you evaluate the probability of z greater than 2? No one wants to speak? Okay. Since I want to get through many examples, I'll also try to say the answer. So probability of z greater than 2 is nothing but 2 to infinity 1 over square root of 2 pi exponent of minus beta squared over 2 d beta. This is nothing but 0 to infinity minus 0 to 2 or 0.5 minus 0 to 2 of this function, which you can read up from the table. So can you look at the table and say what is 0 to 2 of integral exponent of minus beta squared over 2 d beta?
0.4772.
Thank you. 0.4772 from the table. Page 127. So if I do the subtraction, that is 8, 0, I'm sorry, 8, 2, 2, 0. 0.0228 or 2.28%. So x is greater than 80 microns 2.28% of the time. So this is the answer. Oops, sorry. I don't know how I okay. I think now we are back. Yeah, okay. So x is greater than 80 microns for 2.28% of the time. That's the answer to the original question. Compute the probability of a measured value being greater than 80 microns. Now we are also asked next, compute the probability of a measured value being between 50 and 80 microns. So how would you do that? I suggest that you try this on your own and then look up. I'll have it ready so that we can compare our answers. Okay. So try on your own. Probability of, sorry?
I have a question about the previous problem. So how do we get to z was less than 2? The z, yeah.
So if you want to write if you define z as x minus x bar divided by sigma x, if you want to say if my x assumes a value of 80 microns, then what is the value of z? To get that, you just substitute x equal to 80. 80 minus 20 is 60. 60 divided by 30 is 2.
Okay, thank you. That makes sense.
Yeah. So 80 minus 20 divided by 30, which is equal to 2. So it's like asking if x takes a value of something, what is the scaled value of x, which is nothing but z. So if I go for probability that x assumes values between 50 and 80 microns, it's like asking probability of, so this is an inequality. So I can subtract 20 microns or the mean from each step or from each side. So I can write 50 minus 20 less than x minus x bar less than 80 minus 20. And then I can also divide throughout by the standard deviation. So what is this? 50 minus 20 is 30 microns divided by 30 microns, which is the standard deviation. X minus x bar divided by sigma x is less than 60 microns divided by 20 microns. That is nothing but probability of z assuming values between 1 and 2. So that's how I went from quantity with units to a quantity without units. That is, x is the quantity with unit and z is the corresponding scaled version of that quantity without units. So if you want to answer this probability, it is equivalent to answering this. So this is easy to look up. Just look up table 4.3. And once you have the answer, it is the same for the original problem. So the theme is always to reduce a given problem to the standard normal distribution. That's it. So now, if you want to look up the probability of z taking values between 1 to 2, that is easy. This is the probability of, this is 0 to 2 of 1 over square root of 2 pi exponent of, this is, strictly speaking, this is square root of 1 over 2 pi exponent of minus beta squared over 2 d beta, and I can split this as 0 to 2 minus 0 to 1, which is what we did in class, and we made the arguments about subtracting the areas. So if you draw the bell curve, this is z 1 2. What we want is the shaded area. Can you look up this from the table and tell me?
So that one is 0.4772.
72 minus
0.3413.
correct? If you look up for 1.00, that is 3413. Yeah, okay. So that is 9, 6 minus 1, 5, 7 minus 4, 3, 4 minus 3, 1. So that is 13.59%. So about 13.5% of the time, z is between 1 and 2, or in other words of the original problem, x, the diameter, is between 50 microns and 80 microns. Talon, Sailor, is it making sense?
Yes, sir, it is.
Yes,
It
okay,
is.
good. Okay, thank you. Yeah. All right, so we just did one example, like there is kind of the template example for this type of problems. Let's do a few more. So I copied these from another textbook. If you see the problem 24 here, let x be a normal variable or normally distributed variable with a mean of 14 and variance of 4. So let's say mean of 14 and variance sigma x squared is 4, or sigma x is 2. Always variance is nothing but standard deviation squared. I don't know why this keeps happening. Okay, just give me 1 second, I'll fix it. Hopefully it won't happen. Variance is equal to standard deviation squared, or you can think of it the other way also. It's fine. All right. So given this mean and variance, determine C such that the probability of X less than or equal to C is 95%. So what they're asking is this. If X, nothing is said about X, we'll assume that X can vary all the way from minus infinity to plus infinity. So they are asking, if I draw the bell curve with the mean at X bar, and what they want to find out is, they want to find the value of C such that everything to the left of C, the area to the left of C or the probability to the left of C is 95%. Okay. So this is given in terms of a mean and standard deviation. Yeah, this is given in terms of a mean and standard deviation. So your first step is to convert. Your first step is to convert a problem, or convert the given normal distribution into the standard normal distribution What's the difference? Any normal distribution has a mean and standard deviation. Standard normal distribution is a special case with a mean of 0, and standard deviation of 1. Okay. And how do you do that conversion? So if you have a variable x, okay, x minus x bar divided by sigma x, we'll define it as z, where x is the normal variable and z is the standard normal variable. So to convert any problem, the cheat sheet, or the simple trick, is to just write this table. Say first start with literally writing this down: x minus x bar divided by sigma x equal to z. If x equal to some value, then substitute a specific value of x into the above to get the corresponding value of z. Simple. Now the problem is actually asked here in the inverse. That is, we are asked to say what value of c has 95% of the area under the graph, or 95% of the probability. So you can start by looking up table 4.3 for the value of z which up to which the probability or area under the curve is 95% or 0.95 is 0.95. Okay. So if you have that table 4.3 in front of you, look at it and tell me how you will do this. Look at that figure in the bottom, figure 4.3. Look at the table and tell me how you will figure out the value of Z for which the area is 0.95. So this is figure 4.3. Now, only the right-hand side is given in that figure, assuming that the left-hand side is just 0.5. That is, it is symmetric. So minus infinity to 0 is 0.5. 0 to infinity is another 0.5. Now, if you want 0.95, okay, clearly you want to start from minus infinity all the way to C, all the way to some value for which the area under the curve is 0.95. Clearly, if you go from minus infinity to 0, this portion is 0.5. So if you subtract that 0.5, this portion is 0.45. So you need to look up what value of Z will get you 0.45 approximately.
I see 1.64.
1.64 and 1.65, they are just exactly so you can say do like a quick linear interpolation and say it is 1.645 approximately. Z is approximately 1.645. Others who are trying, Kim, Sailor, Talon, are you able to agree with me?
Yep. Looks good to me.
Looks
Yes.
good. So you just have to look at the original statement, which says the probability of X up to C is 0.95. So we converted the problem in terms of Z and looked up what value of Z leads to 0.95, which is 1.645. So now the problem is not yet over. You still have to convert this Z value back to the X value. Now recall that Z equal to, oh, this is so annoying. Please don't tell me I lost everything. Yeah, I didn't lose much. So we just wrote that the value of Z to get 0.95 is 1.645. Now we want to recall that Z equal to X minus X bar divided by sigma. So if this is 1.645 and this is the X we want to figure out, and then we'll call this X95 minus X bar. What was X bar? X bar was 14. The mean is 14 and standard deviation is 2 units. So X 95% is 1.645 times 2 plus 14, which is how much? 10, 9, 12, 3 plus 14 or 17.29. So when X is 17.29, that value encompasses, so this is actually turns out to be 17.29. It encompasses 95% of the probability of X assuming values all the way from minus infinity to 17.29. Does it make sense? Like, are you able to follow? Yes. Okay. Yes, Talon. Thank you. Okay. So now, so Kim, I know you joined a little late. If you have any questions, feel free to stop me and ask. All right. So now let me go back to this slide where I had the problem statements. So now we want to focus on this number 25. Oh, actually, there are a few more things we need to do. So we just did this part. Probability that X assumes values less than C, so that it leads to 95% probability. Now I want us to try probability that X assumes values less than C, that leads to 5% probability. That is, if you go back to this picture, so this is for 95%. We now want to pick value of C such that it leads to 5%. So X taking all values all the way from minus infinity to C, that leads to 5% probability. That'll be interesting. So let me go here, start a slide, and then we want to do what is the value of X, what is the value of C that leads to 5% probability. So first, look up table 4.3 to figure out what value of Z leads to 5% probability. Now, before you do that, it's a little tricky. So let me draw a figure for you. So here is the standard normal distribution with Z equal to 0. Here is the bell curve. Okay. So what they are asking is, what is the value of C that leads to just 5% area? So if you have to think about C being here and this area is 5%, which means everything to the right of it is 95%. So what is the trick I told you yesterday? Hold this like a pivot and flip the page, and you just have to project C back here so that this area is 5%. Or in other words, it's the same as asking what is everything else to the left of C, which is 95%. Which, if you think about it, it's really the same problem. So C is again 17.29. Okay, this value of C is 17.29, but the catch is you are not interested in this C value. You are interested in this value, which leads to 5% probability. So you have to be carefully writing C 5% is minus 17.29. There's a little trick there. You might think that the first problem and second problem have the same answer, but they differ by a negative sign. So take a minute and think and let me know if that makes sense to you. Make sense? Thank you, Sailor. April, Kim, good. Thank you. Thank you. Okay. All right. So yes, good. So clearly, this is all about first drawing a bell curve, marking the positions of the variables, their values, and then shading the area and then doing the problem. So that way, if you do it, it becomes very simple. Actually, it's very simple and very interesting as well. So if you look at the third part, what is the value of C that leads to 99.5% probability? So now they want us to find C 99.5. That is, it should have 99.5% of the probability. So this is very similar to the first case where we want to figure out probability of X less than or equal to C such that this is equal to 99.5%, or if you want to write it as a fraction, 0.995. Okay, so if you look up table 4.3, what value of Z leads to an area of 0.995 minus 0.5. Whenever the probability is more than 50%, make sure that you put it on the diagram and see that usually you will have to subtract the left half, which is 0.5. But again, don't take this as advice for all the time. You have to be careful. That's why I'm asking you to draw the diagram. So this is 0.495. So look up the table and tell me what value of Z gets you approximately 0.495.
It's close to 2.57.
2.57. We'll call it 2.575. Okay. So this is approximately Z is approximately 2.575. Now others, kindly confirm if you also think it's the value to pick. .575. Just have to look up the table and find the value which is closest to 0.495. Okay, so Z is nothing but x minus x bar divided by sigma x. So Z 99.5% is 575, right? 575 equal to x minus what is x bar? I think 14. Sigma x is 2. So x 99.5% is nothing but 2 times 2.575 plus 14. So this is 10, 14, 15, 11, 5 plus 14, or 19.15. 19.15. If you put it on the picture, it will make sense because this is 14. Mean is 14. If you want a value that has 95% of the probability, then 17.29 is that value. And if you want 99.5%, that is 19.15, even further out. And recall that the standard deviation is only 2. So how much is 19 as 19 minus 14? That's about 5, and that's nearly 2.5 standard deviations. Okay. All right. So that's 2.5 standard deviations. Can we move on? Is it making sense so far? Am I rushing it too much? Okay. All right, good. So we have what, for 20 minutes, and we'll see how far we can go. So then the problem 25 should be something that you can attempt on your own. What I'll do is, in the session I planned on Monday, I'll try to briefly go over problem 25. Okay, so you can try that. And if I want to do one example on no, I don't want to do problem 16. It's not something we discussed in the class. All right, so here is one more example which you can use to actually check your work. So we did x less than c for 95%, and we got what did we get? Oh, this is with a different standard deviation, so don't worry about it. But anyway, this problem here asks you to compute the value of c such that x the probability is 95%, and x has a mean of 5 and a variance of 0.02. Then it's nothing but standard deviation of 0.2. So yeah, right here. So if you do this example on your own later, here are the values which you can compare with, and you can actually get the answer and cross check. Okay, so try this example later. All right, so this one I want to try now. In a production of iron rods, let the diameter x be normally distributed with a mean of 2 inches and standard deviation of 0.008 inches. What percentage of defectives can we expect if we set the tolerance limits at 0.02 inches? That is, anything larger than 2.02 or anything smaller than 1.98 is considered defective. Okay. Okay. Just 1 second. I have to silence a child. It's just being very loud and it's disturbing me. I'll be back in 1 second. All right, I'm back. So what percentage of defectives can we expect if we set the tolerance limits at 2 plus minus 0.02 inches? So exactly putting in symbols what I said, anything less than 1.98 and anything more than 2.02 is considered defective. If you want to consider either, like if you want to calculate probability of x greater than 2.02 plus the probability of x less than 1.98, that is same as asking what is the probability of 1.98 to 2.02 and subtracting it from 1. So they first get the success probability and then subtract this from 1. So if you say what percentage of defectives, it is basically 98 and a 3/4. 100 minus 98 and a 3/4%, which is 1 and a 1/4% as given here. Of course, you can what I want you to do is go through these steps where the value of x is 2.02. So this exactly here is x minus x bar divided by sigma x. This being x bar, this being sigma x. And we are asked to calculate what is the value of x between 1.98 and 2.02. So you first scale it into the z value and then compute it from the table to get this probability. Now, may I ask you guys, do you think you would be able to do this and later check, or would you like me to do the steps and we can see it in the end? Okay, since I'm not getting any answer, since the solution is right here, for whoever's watching the recording, please go through the solution. And if it is not clear, we can go over this again on Monday, like just to do the steps and reinforce it. All right, so as far as the problems I wanted to do are concerned, those are the ones I planned. Is there any specific questions or problems that you want me to try? Nothing, Kim? The X mark I denotes means nothing specific. Okay, so that's fine. So let's, I don't know if the same group will be there on Monday, but on Monday I plan to do basically examples, 2 examples on ODEs and maybe 2 examples on statistics. Okay, so in the time that I do have now, which is about 15 minutes, let me try to do an example on ordinary differential equations. Okay. All right, so in the class as well as in the previous sessions, we did one problem that is, we did one type, which is first order differential equation. And then we did one type, which is simultaneous equations. Let me pull up that. Yeah, we did one type, which is simultaneous equations. And we can also try one example in which we have a second order differential equation where you first get a second derivative and then you make the substitution that dy by dt equal to z, which reduces the problem to two first order differential equations. And then you can solve it just like you would do 2 equations. So this is the example I think given in the homework. So we attempted or set it up, and maybe we'll try to do a case study now. Try to pick one problem that is from chapter 28 of the book. Effective mean. Yeah. Sorry, not chapter. Yeah, chapter 28. That's correct. 28. So let's do, if you have the textbook in front of you, Problem 28.8 from the textbook. Let me share my screen here for a second. Problem 28.8 from the textbook. So I'll give you a moment to read the problem, then we'll continue. Compound A diffuses through a 4 centimeter long tube and reacts as it diffuses. The governing equation for diffusion with reaction is D multiplied by d squared A over dx squared minus K times A equal to 0. So this is the diffusion term, and this is the reaction term. Of course, you don't need to know all that. What you need to do is be able to read the problem. At one end of the tube, there is a large source of A at a concentration of 0.1 moles. So if we set up a domain, which is x equal to 0 and x equal to L, at x equal to 0, there is a concentration of 0.1 moles. So A value here is 0.1 moles. At the other end, there is an adsorbent material that quickly makes quickly absorbs any A, making the concentration as 0 moles. If D and K are given to you with units, what is the concentration of A as a function of distance in the tube? Okay. Wait, is this what we want to do? No, this is a boundary value problem. We want to do initial value problems. Sorry for wasting your time. We don't want to do this problem. Yeah, let's try this 28.11. That is a time dependent problem. Okay, so strike this. Problem 28.11. Okay, so you have a non-isothermal batch reactor that can be described as, you have dC over dt given as exponent of or minus e power minus 10 divided by t plus 273 multiplied by C. And then the temperature itself is a function of time. So you have 1000 exponent of minus 10 divided by t plus 273 multiplied by C minus 10 times t minus 20. It's looking very complicated, but what I want you to take away is that this equation in C depends on both temperature and concentration, and this equation for temperature depends also on temperature and concentration. So if you call this f of t temperature and concentration, and you call this h of time temperature and concentration. The only thing is time does not explicitly appear on the right side of both the equations. So it is not an explicit function of time. It only depends on temperature and concentration. Okay, which is what you're trying to solve for. So I'm going to bring back my writing pad. Okay, so just 1 second here. All right. So here is my equation. Okay, so I'm going to write dC of dt is equal to f of time comma temperature, comma C. Of course, it doesn't explicitly depend on time. dt over dt is g of time, temperature, concentration, doesn't depend on time. Okay. And then the concentration value at time 0 is given to be 1 gram mole per liter. And the temperature value at time 0 is 15 degrees Celsius. Find the concentration of and temperature of the reactor as a function of time. Now, don't be scared. It's not for all of time that you are asked to do. In the exam, I won't ask you for more than maybe 2 or 3, usually 2. That is, if you have time 0, 1 time step, 1 more time step. That's it. Okay. So let's think about what time step we want to use. So we'll just try to say, or I'll usually give the time step in the exam. So for now, we'll just say we'll do this with 0.5 second time step. So you need to pick a method. If nothing is told to you, you can pick any method that you want. Usually I'll tell what method to use. Say the simplest method is Euler's method, which is dy by dt equals f of t comma y, says yi plus 1 or y at the next time step is y at the current time step plus the function t at the current time multiplied by dt. This is the Euler's method, the simplest method there is. Okay. So what we want to do for this problem is to write c at the next time step is the value of c at the current time step plus delta t multiplied by f of t, temperature and concentration. And same thing for temperature, t of t plus delta t multiplied by g of temperature and concentration. Now the both of you just try to look at this and tell me if this step makes sense to you, because if it does, next step is just plugging in numbers. Yeah, April, thank you. Okay. So since we are nearing the end of the hour, what I will ask you to do is substitute t equal to 0 in f and g and put them here. Okay. And then you want to also use delta t equals 0.5 seconds. So if you put t equals 0, then you'll have to say time 0, temperature at time 0, and concentration at time 0. Okay. Now those are just initial conditions. These are all given to you. Okay. So you go back here. This is your f, the function f, and this is your function g. Okay. In here you have to use temperature at time 0 and concentration at time 0, which is what? Temperature at time 0 is 15 degrees Celsius and concentration at time 0 is 0.1 gram moles per liter. So you have to substitute in the function, get the values, and then you have to use it to compute the next step and so on. Okay. So since I'm about end of time here, I'll stop here and maybe Monday we'll try to do this little more completely. Okay. So I'm going to close this file. So before we go, any questions? April, Kim?
So on the test, we'll either have a and or a first or second order ODE and not third.
No third, never
Okay.
third. Okay. Either you will have a second order ODE or you will have a system of two ODEs, which is really the same. A second order ODE reduces to a system of two first order ODEs, or you'll be just given a problem like this one, two first order ODEs that are coupled to each other. That's it. Only those two are possible. So there will be two problems on the topic of differential equations, numerical methods. One, solving a first order differential equation using RK4 method, and the other problem will be solving either a second order differential equation or a system of two differential equations using a simpler method like Euler method or second order RK method. Okay.
Thanks.
Right.
Can
So
you,
yeah.
So the test will have 4 questions, is that correct?
4 questions.
The other 2 will be the statistical questions?
Yes.
Okay.
It will follow the template as posted in the mock exam that is on Canvas. I posted it yesterday itself. So if you look at it, 4 questions, all the information necessary for each question will be given. So you don't have to bring any sheet or anything.
Okay, thank you.
Yeah. All right. Thank you for coming. We'll see you on Monday and Tuesday.
Okay. Bye-bye.
Bye.